Okay, we're going to be talking about empirical formulas today. So we want to review percent composition. Um, that is the percent by mass of each element in a compound. All right, composition is what something's made of. So percent by mass, anytime you're doing a percent, you've got the part compared to the whole. So the mass of your one element compared to the mass of the whole compound. That gives you a decimal. To make that into a percent, you times by 100. Right, just like we did percent error and percent yield. All right. So what is the percentage of hydrogen right here? So we're going to look at how much hydrogen we have. We have 6 hydrogen molecules, right? And each one is 1 gram. So that would be 6 grams, all right? And then I've got, I want to look at carbon. So I also have 6 carbons, so I'll say 6 carbons, and each carbon is 12 grams. So I'm going to say that would be 72. All right, and if I want the total molecular mass of this molecule, I'm going to add that together. So that would be 78 grams per mole. All right, so if I want the percentage of hydrogen, all right, well, that would be how much hydrogen I have. I have 6 divided by the whole. So the part divided by the whole is 78. And that gives me a decimal. Then I'm going to times that by 100. All right. So let me just do that on my calculator. 6 divided by 78. So I have 6 divided by 78. And then I'll multiply that by 100, which just moves the decimal over. Oops. 2. So 7.69. Oh, shoot. I just lost. Hang on. Let me find my, oh, here we go. Okay. So here we go. That would be B. We just want to find the closest answer because I was rounding off. So it's going to be a little different than if I had done the exact decimals. All right, so here we want the percent of oxygen in water. So notice we just figure out, well, I've got 1 oxygen, so that would be 16, right? The whole mass of the water would be 18, right? Because it's 16 for the oxygen, plus you have 2 hydrogens, right? So it's 16, 17, 18. All right, you times that by 100, and then that gives you your answer. 16 divided by 18. So 16 divided by 18 times 100. So 88.9%, we'll say. So the percentage of oxygen, so same thing, percentage of oxygen, but we have a different molecule, all right? So let's see how much oxygen we've got. I've got 1 calcium, Says I have two hydroxides, right? That's what this means, two hydroxides. So if I have two hydroxides, that means I have two oxygens, 1, 2, right? So this 2 kind of gets distributed here. So I have oxygen, I have two oxygens, and I know each one is 16 grams. Calcium, I just have one, all right? And I would look on the periodic table. Let me just check to be sure. Where's my periodic table? All right, so calcium is 40 grams. Oops, I don't want to go there. All right, so, and then the hydrogen, again, I have two of them, 1, 2, right? The 2 gets distributed here, so I have two hydrogens. Each one is 1. Right, going to multiply those out. So 1 times 40 is 40. 2 times 16 is 32. 2 times 1 is 2. And I add that up, so I get 74 grams per mole of my calcium hydroxide. All right. So, and it's kind of nice because I've already figured out then how much oxygen I've got. I've got 32. So I just, anytime you do percents, you're just comparing the part to the whole. And that gives you a decimal, so we move it over 2 times. All right, so 32 divided by 74 times 100. All right, so I get 43.2%. Actually, I'll go ahead and take it out 2 places. If I take it out 2 places, that would be 24. 24%. All right. Very good. So now we're going to find the percentage of sulfur. So let's find the total molar mass. I've got hydrogen, sulfur, and oxygen. I've got 2 hydrogens, 1 sulfur, and 4 oxygens. Hydrogen is 1 gram, sulfur is 32. And oxygen, again, you get these from the periodic table. So we're multiplying, right? So 2 times 1 is 2. 1 times 32 is 32. 4 times 16 is 64. I'm going to add them to get the total molar mass. So that would be 98 grams per mole. All right. And I figured out how much sulfur I've got, so I'm just going to divide 32 by 98 and times by 100. So let's see, 32 divided by 98 divided by 98, oops, times 100. So that's about 32%, which makes sense because 98 is like 100. So 32.65. So 32.65%. All right, if I wanted to be very precise. All right, awesome. What is the percentage of oxygen? We have calcium nitrate. All right, so I've got calcium, nitrogen, and oxygen. I have 1 calcium, 2 times 1 is 2, and 2 times 3 is 6, right? Because that says I have 2, this is in parentheses, so I have 2 nitrates. There's 1 nitrate, here's 2 nitrates. So I have 2 nitrogens, and I have 3 plus 3, I have 6 oxygens. All right, so now what's the mass of each one? So calcium, I think we said, was 40. Nitrogen is 14. And oxygen is 16. And you get those from the periodic table. We'll multiply. 1 times 40 is 40. 2 times 14 is 28. And 6 times 16 is 96. And I'm going to add them together. So that would be 14. So 9, 10, that's 16, 164. And that would be grams per mole. All right. And so now it says percentage of oxygen. So that would be, here's my oxygen, right? So it's going to be 96 divided by the part divided by the whole, 164 times 100. So 96 divided by 164. 96 divided by 164 times 100. 58.53. And that is my answer. Now that is, we're done practicing with composition, all right? Present composition. So now we can talk about empirical formulas and molecular formulas. Well, empirical formulas are just the reduced formula for a molecular compound, all right? We're talking about the reduced ratio. Remember in the molecular formula, the subscripts tell you the ratio of the atoms. So in an imperial one, you just have the reduced ratio. So let's see what that means. So I have, this is my molecular formula, all right? And they're both even. Both my subscripts are even. 4 is even, 10 is even. So that means 2 goes into both of them. 4 divided by 2 is 2. 10 divided by 2 is 5. So there we go. This would be the empirical formula because it's reduced. And the molecular formula is not reduced. All right. If you have even numbers, you know that 2 is a factor, is a common factor. So here we go. What is the empirical formula? So we want the reduced ratio. So I've got 2 to 4. So they're both even. So I can divide both of them by 2, right? My original ratio of nitrogen to oxygen is 2 to 4. Well, they're both even, so if I divide 2 divided by 2, that's 1, and 4 divided by 2 is 2. So that reduces to a fraction of 1/2, 1 to 2. So that would be this guy. And that's the lowest you can go, 1 to 2. All right. Diphosphorus hexoxide. So that would be, remember di means 2. So that would be phosphorus, and I have 2 of them. Hex means 6, and then oxide would be oxygen. So I have 6 oxygens, right? So this would be a, got a non-metal. So this is a covalent compound. That's why we have the prefixes there. So the ratio then of phosphorus to oxygen is 2 to 6. All right, so they're both even. That means I can reduce it. I can divide both of them by 2. 2 divided by 2 is 1. 6 divided by 2 is 3. So the ratio, the lowest reduced ratio would be 1 to 3. So that would be this guy. Now we're given the empirical formula, right? So it says, which of the following could be the molecular formula? All right, so the ratio there has to be of carbon to hydrogen has to be 1 to 2. All right, so there could be more than one answer. All right, let's see, if I have 2 to 6, well, that means that the carbons were doubled, right? 1 times 2 is 2, right? But if I double this one, right, that would be 4. So if I have 2 carbons, I have to have 4 hydrogens to keep this 1 to 2 ratio, okay? Just like you do in geometry with your similar polygons. All right, so if my ratio is 1 to 2, the other one has to be 2 to 4. So that is out. If I have 6 carbons, right? Let's say I have 6 carbons. Well, that was 1 times 6, right? That was 6 times bigger. So that means this has to be, I have to have 6 times as many hydrogens. I have 6 times as many carbons, so 2 times 6 would be 12. All right, and so that is not a choice. So this has 6 to 6, that would be like a 1 to 1 ratio. This one is 2 to 1, right? A lot of people will pick this one because they see the 3, 6, and oh, that reduces to 1/2, but this is saying I have 6 carbons. According to this, you always have twice as many hydrogens. The hydrogens is always more, twice as much. Okay, so this is out because that's half. So that would have to be my 4 to 8. So that's saying if I have 4 carbons, right, then 4 times as many, right? So that means 2 times 4 would be 8. All right, 4 divided by 8 reduces to 1 to 2. All right, so now I have sulfur monoxide. All right, so this is another covalent compound. There's my sulfur. Mono means 1, so I have 1 oxygen. So the empirical formula is has a ratio of 1 to 1. 1 sulfur, 1 oxygen. So let's see, this has disulfur dioxide. Well, that would be 2 to 2. And that is the same thing, right? Basically 1 to 1 means they have to be the same. 2 to 2, right? I double the sulfur, I double the oxygen, right? So that works out. Notice it says select all that applies. So you can have more than one molecular formula. B is trioxygen trifluoride. Oh, that can't be it. That's a whole different, the tris are both the same, right? But this is oxygen and fluoride. So that is not the same molecule. Tetrasulfur pentaoxide. So that's 4 and 5. So that doesn't work. All right, if you have 4 to 5, that's not the same, that's not equal. That's not a 1 to 1 ratio. Hexasulfur hexoxide. All right, so I've got the right elements, right? Sulfur and oxygen, so that's good. And then I've got 6 sulfurs and 6 oxygens. Well, 6 to 6 is the same as 1 to 1. If you multiply this by 6, you multiply this by 6, it's going to be the same thing. So these are my 2 molecular formulas that reduce to this, sulfur monoxide. So that is the basics of empirical formulas compared to molecular formulas. And you'll see in the practice there are different kinds of problems that you can work with knowing that. All right, good luck.